Faced with mounting death tolls on their highways, many states are passing laws requiring people to wear seatbelts. Do these laws work? In North Carolina, the severe injury and death rate in car accidents dropped from 4.7% to 3.8% after a seatbelt law was passed. That's a lower rate, all right, but not a lot lower. Since there is random variation, could the decreased rate after the passage of the seatbelt law been the result of chance? Statistics can clarify ambiguous findings like these. In this case, we can use something called a test of significance to measure precisely the probability of getting that change in death toll purely by chance. In this program, we'll learn that significance tests are among the most widespread tools of statistical inference. We'll learn about the p-value, which tells us how strong our evidence really is. And we'll learn what the potent phrase statistically significant means and what it doesn't mean. In the last program, we saw that confidence intervals are used to estimate a population parameter from a sample. Tests of significance make up the other major class of inference, and they're aimed at a different goal. Significance tests let us see whether a given result is likely to be due to chance or whether some other factor seems to be at work. By using a significance test, statisticians found that a drop in the serious accident rate as large as the one in North Carolina would happen less than 3 times in 100 if random variation was the only reason for the change. That's pretty unlikely, so it's strong evidence that the seatbelt law saves lives. This example illustrates the reasoning behind all tests of significance. First, we assume that nothing unusual is going on. Then we find out how likely it is that our result could have occurred purely by chance. If the result is very unlikely, we have reason to believe that something is going on. In a test of significance, the assumption that nothing's going on, that there is no effect, is called the null hypothesis. It's written as H0. We also need to create an alternative to the null hypothesis, which formally states that something is going on. It's called, logically enough, the alternative hypothesis, and it's written as HA. So in a significance test, we compare an observation to what we would expect to observe if there really was no effect. This comparison gives us evidence either for or against the null hypothesis. And speaking of comparisons...
Shall I compare thee to a summer's day? Thou art more lovely and more temperate. Rough winds do shake the darling buds of May, and summer's lease hath all too short a date.
The immortal words of William Shakespeare still ring with eloquence and beauty centuries after he wrote them.
Shall I die? Shall I fly, lovers, baits, and deceits, sorrow breeding? Shall I fend? Shall I send? Shall I...
What about this poem? Aesthetically, it doesn't seem like Shakespeare, but there is strong historical evidence suggesting that the poem is in fact by Shakespeare. Can statistics help decide the poem's authorship? In 1985, while conducting research for an edition of the complete works of William Shakespeare, scholar Gary Taylor found this poem in an obscure manuscript in the Bodleian Library of Oxford. Taylor had never heard of the poem or seen any references to it, so he was quite surprised to see that the scribe copying the manuscript had written a familiar name at the end.
What matters about the poem is that at the bottom of it is written William Shakespeare. It's attributed to him. And this is clearly written in the same ink and at the same time as the rest of the poem. And so then it was just a matter of deciphering the handwriting and producing a transcript of the poem, which I could then take back to my office and begin to investigate.
Taylor and his colleagues were eager to include the newly discovered poem in their edition of the complete works. But first, they publicized it to see if anyone could produce evidence that it wasn't Shakespeare. The poem generated a storm of controversy. Those who accepted Shakespeare as the author were excited by the find, the first new work discovered in centuries. Others claimed that the poem was not good enough to be by Shakespeare.
This PJ...
The debate caught the attention of University of Chicago professor and statistician Ron Thisted. A decade earlier, Thisted and his teacher Bradley Efron had done a statistical analysis of Shakespeare's vocabulary. Their work was an extension of a difficult problem in statistics. In this case, they wanted to know how many words did Shakespeare know but never use. It was, they thought at the time, purely an academic exercise.
We certainly had no expectation that we would ever be able to put our mathematical description of Shakespeare to any use. After all, there had been no new Shakespeare discovered for several hundred years, and there was no prospect of any new Shakespeare being discovered. And so for us, it was, Shakespeare was really an interesting illustration of the basic statistical ideas that we developed.
Thisted's model provides a detailed numerical description of Shakespeare's vocabulary, the starting point for addressing the authorship question. For any work, Thisted can tell how many new words there are that Shakespeare never used before, how many words that he had used only once, twice, and so on. Based on this model, he was able to predict that if Shakespeare had written the poem, Shall I Die, there should be 7 new words in it. In fact, there are 10 new words in the poem. Does this difference just reflect random variation in Shakespeare's writing, or does it prove that Shakespeare did not write the poem? Significance testing can help answer this question.
There were 3 more words, 3 more new words in the poem than our model predicted. Now the question then, is that 3-word difference a big difference or a small difference? And the way to answer that question is to compare the difference to some measure of how much variability there would be from one poem to another of this size. That's the information the standard deviation gives you. And the standard deviation of about 2.6 here says that the difference we've observed is slightly more than 1 standard deviation on the high side, which is in itself not very different. It's within the range of variability we expect to see.
Yet I must vent my lust and explain inward pain.
In the formal language of significance testing, Thisted's null hypothesis was that Shakespeare wrote the poem. By comparing the difference between the observed number of new words, 10, and the predicted number of new words, 7, he was trying to find evidence against the null hypothesis. In fact, since the difference is just over 1 standard deviation, he could expect to find a value as extreme as 10 new words about 25% of the time. He therefore failed to find convincing evidence against the null hypothesis that Shakespeare actually wrote the poem. But, and this is an essential thing to remember about significance testing, this does not prove that Shakespeare wrote the poem. It only fails to prove that he did not write the poem.
What we could have hoped for, perhaps, was that such a bad poem would have been clearly non-Shakespearean, in which case we could have disproven the Shakespeare hypothesis. But like a paternity test, it can only rule out, it can't rule in.
Meanwhile, Taylor was involved in a very different kind of pursuit, but one which was yielding similar results. He was comparing the poem's stylistic elements, its rhyming scheme and imagery, to other works by Shakespeare. Like Thisted's statistical work, Taylor's literary work failed to uncover evidence against the null hypothesis. He saw no reason to reject the evidence provided by the historical witness, the 17th century scribe who attributed the poem to Shakespeare.
We have historical evidence that says it's by Shakespeare. And so in a way, the burden of proof is on the people who want to say it isn't by Shakespeare, because they have to contradict that early 17th century witness. All that the supporters of Shakespeare's authorship have to do is to prove in as many ways as they can, as many different tests as they can, that this could be by Shakespeare, and therefore there's no strong reason to doubt what the witness says.
In the absence of statistical or literary evidence disproving the historical record, the poem, now titled A Song, was included in the complete works.
Shall I die? Shall I fly, lovers, baits, and deceits, sorrow breeding? Shall I fend?
To get a clearer idea of how significance tests work, let's walk through an example based on the story we just saw. Since we want to work with sample means, we'll alter the scenario a bit and suppose that 5 new poems were found. That means that instead of a single count of new words in one poem, we would find the average number of new words for the 5 poems. Let's say the average was 8.2 new words per poem. We know from research into Shakespeare's collected works that the mean number of new words in poems of this length is about 6.9. But the mean X bar of new words in this new group of poems is 8.2. Can we conclude on this evidence that Shakespeare didn't write them? The null hypothesis in our case is that Shakespeare really wrote the poems. In other words, we'll assume that our result of 8.2 new words per poem reflects nothing more than normal variation in Shakespeare's writing. Now, we need to express our null hypothesis numerically, so we'll couch the statement in terms of the population mean. Our null hypothesis says that the mean of the population from which the sample was drawn equals 6.9 new words. The alternative hypothesis says that the mean of the population from which the sample was drawn is not equal to 6.9. The alternative hypothesis is a compact way of saying we suspect the poems were written by another author. Notice, the null and alternative hypotheses are always stated in terms of population parameters, not sample statistics. There's one more thing to keep in mind when you're setting up your significance test. You have to decide whether to use a one-sided or two-sided alternative hypothesis. This means you have to decide whether you're interested in results falling on only one side of the mean or on both sides. In our case, it's clear that another author might consistently use either more or fewer new words than Shakespeare. So the alternative hypothesis is two-sided. On the other hand, suppose we suspected that the poems had been written by a specific author known to use more new words than Shakespeare. Then the alternative hypothesis would be one-sided. In general, it's smart to use a two-sided test unless you're absolutely certain that you're only interested in values in one direction. So we start by assuming the null hypothesis is true. Then we find the probability of getting a result as extreme as ours if the null hypothesis really is true. When that probability is small, we reject the null hypothesis and accept the alternative hypothesis as plausible. How do we find this probability? We go back to the distribution of a sample mean, X bar. Here's the distribution of the number of new words in a Shakespeare poem. It's normal with a mean of 6.9 and a standard deviation of 2.7. So if we form the distribution of X bar for samples of 5 poems, the mean is still 6.9, and now the standard deviation is 2.7 over the square root of 5, or 1.21. The mean of our 5 mystery poems is here at 8.2. That's our observed X bar, which is 1.3 above the population mean of 6.9. We want the probability that 5 Shakespeare poems would have an X bar at least this far, or farther, in either direction from 6.9. That's an X bar above 8.2, or below 5.6. We want the probability in both directions because our alternative hypothesis is two-sided. We know how to do this normal probability calculation. We standardize the distribution of X bar to obtain the familiar Z. The ingredients of Z are the observed X bar, the population mean mu given by the null hypothesis, the standard deviation of the population, and the size of the sample. Z is essentially a measure of the distance of X bar from the hypothesized mean. We call Z the test statistic. Now we can plug in the following numbers. X bar is the average new word use in our 5 poems, 8.2. Mu given by the null hypothesis is the population mean, which is 6.9. The standard deviation of the population is 2.7, and the sample size is 5. Doing the math gives us a z of 1.08, a bit more than one standard deviation from the mean on the standardized normal curve. That's the observed value of our test statistic. The final step in our test of significance is to find the probability of a z at least this extreme. This probability is called the p-value. Remember that we're looking for the probability that corresponds to the regions under the tails of the curve. To find this p-value, we use the value of z that we found before. That was 1.08. From the z table, we see that the area below 1.08 is 0.8599, which means that 0.1401 is left in the tail. To find our p-value, we double this area because we're interested in the area under both tails of the curve. Our final result, 0.2802, is the p-value we've been looking for. There's a 28% chance that random variation would produce a mean new word count as far as 8.2 from Shakespeare's usual count. That's a pretty good chance. We could expect a result like that about 1 time out of 4. And that means we've failed to reject the null hypothesis. We did not find good evidence against Shakespeare's authorship. This is an example of the general rule about p-values. Small p-values represent evidence against the null hypothesis. Large p-values fail to give evidence against the null hypothesis. For instance, suppose we had found a small p-value, say 0.04. That would have meant that there was only a 4% chance that 5 poems by Shakespeare would produce an average number of new words this far from his usual 6.9. We would have good reason, then, to suspect that something else was at work, namely a poet other than Shakespeare. Since p-values can range from the minuscule to the very large, researchers and scientists are often faced with a dilemma. Does a particular p-value give enough evidence to reject the null hypothesis? With a p-value of 1 in 1,000, there's little question that the null hypothesis is wrong. But what about 1 in 50 or 1 in 10? It's because researchers have so often come up against this type of problem that several fixed levels for p-values are commonly used. The most widespread is 0.05. That means a result could be expected to occur only 5% of the time, or 1 time in 20, if the null hypothesis was true. Statistically significant at the 5% level simply means that the results produced a p-value less than 0.05 and were therefore considered significant. A significance level of 0.01 would mean that a result could have been expected to occur by chance only 1 time in 100. It's important to pick a p-value appropriate to the situation. For example, suppose you're doing research on a new cancer therapy. Because of the possible consequences of recommending the treatment to thousands of patients, you may feel that a 0.05 significance level is not good enough. Here, you need to be more certain that the therapy works. You decide to call your results significant only if they reach the 0.01 level. There really is no sharp border between significant and insignificant results, only increasingly strong evidence as the p-value decreases. You should ask what the precise p-value is, because that will be the best indication of the strength of the evidence. The power of significance tests to weigh evidence has led to their widespread use in courtrooms, especially in discrimination cases.
One doesn't go against the FBI. It's very anti-American, it's anti-patriotic, people think you're crazy to go against the FBI. Yet I knew that my rights were being violated. I knew that this was more than an individual case. What had happened to me had happened and was happening to other Hispanics.
Matt Perez is taking aim against racial discrimination in the FBI. He says it caused his demotion from the FBI's highest-ranking Hispanic agent to assistant in charge in El Paso, Texas. Perez and over 300 Hispanic agents sued the FBI in a class-action lawsuit, charging systematic discrimination in promotions, assignments, and disciplinary actions.
People were being put into what we call the taco circuit, meaning the trenches, the work that was not career-enhancing. we'd get a pat on the head, we'd get a monetary reward now and then for a good arrest, a good takedown, a good case. Yet when it came time to being supervisors, those things were relegated for the non-Spanish speakers and basically white Anglo males.
Multiple rounds of gunfire being fired down the street.
All FBI agents face a range of extremes in their jobs.
4 FBI agents down, 2 or 45.
From life-threatening undercover operations to routine surveillance. The question was, if Perez and other Hispanics had the same skills and the same training as Anglo agents and were performing just as well in their jobs, why were they not being promoted or given choice assignments as the Hispanics charged?
There are performance appraisals that are done. Okay.
Statistician Gary Lafree joined Perez's lawyers as they gathered both anecdotal evidence, individual stories of discrimination, and statistical evidence. Using significance tests, the statistics might show that what was happening was far from coincidence.
So we're talking mostly about...
I concentrated on a snapshot of where the FBI is in 1987. The analysis, though, had to be dictated in part by the fact that we had a very small sample of Hispanics, and a lot of the questions we were interested in had to do with differences between grades and between different ranks. So I was looking for a relatively straightforward approach that would allow us to compare groups, and hopefully that it will allow us to keep a fairly aggregate group so that we could do something meaningful statistically.
Dr. Lafree came to Washington to gather data from the computers at FBI headquarters. Using the same information, but asking very different questions, was the statistician hired by the FBI to assist in their fact-finding, Dr. Rebecca Clem. Her analysis was aimed at answering the question of whether the FBI was changing for the better over time.
The statistics provide a discussion of pattern and practice of an organization, and particularly of their decisions. Generally, the cases I work on are rather large, and so it's not like one decision is being questioned. But it's a series of questions over time that were across different subparts of an organization to see whether there is some systematic pattern of something that is illegal going on.
What she was doing is using a baseline from the past to determine whether there's discrimination in the present. Now, this makes sense that there was no discrimination in the past, but saying, for example, that things are better in 1988 than they were in 1968 is a different issue than whether they're where they should be in 1988.
The case entered federal court before Judge Lucius Bunton. Like most judges who hear class action suits, he knew that both sides would be armed with statistical arguments.
All rise, please.
Statistics are very much a part of the judicial game. I like numbers. They mean some things to me. It's a method of comparison. What you've got to be very careful of, and or at least what I look for, are the assumptions that go into the building of this picture that they're trying to paint for you. Because that's what statistics do. They paint a picture for the judge.
The picture Dr. Clem painted in the courtroom, based on her analysis of change over time, was one of progress in the FBI.
My testimony, from what my findings were, is that there was no problem in Hispanics in being promoted. As a matter of fact, they were promoted faster.
Perez's lawyers used Dr. Lafree's analysis to show a very different effect, that Hispanics were not fairly represented in management ranks.
You're drawing from a population in the United States that's roughly 8 or 9% Hispanic. About 4.3% of all special agents are Hispanic. About, when you get up to the supervisory levels, you're getting around 2%, and when you get up to grades 15, 16 within the organization, the higher supervisory positions, you're down to around 1%. So looking at those differences statistically as a whole, they are statistically significantly different. I pointed out in the courtroom that a lot of the differences were on the magnitude of 1 in 100 or 1 in 1,000.
These p-values were strong, but it was up to Judge Bunton to decide their significance within the surrounding circumstances of the case. Like other judges hearing discrimination suits, he had to balance the numbers with other evidence. In the end, the combination of personal testimonies and statistics presented by the plaintiffs were compelling enough that Judge Bunton found 4 Matt Perez and the 311 class members. With a court victory behind him, Matt Perez gets on with the career he started in 1963, committed to his role within the FBI. The part statistics should play in the courtroom is not so clear-cut, even as important cases which rely on statistical evidence become more common.
There can't be, in a sense, uncertainty in the law. There is a guilty or a not guilty verdict, ultimately. It's a dichotomy. You're either guilty or you're not guilty. And I think that's difficult because in science it's possible, and it's frequently the case, that there is uncertainty, there's gray areas. In fact, that's what statistics are all about, is giving a level of that uncertainty.
As we've just seen, you've got to use significance tests carefully. It's easy nowadays to load data into the computer and let it churn through a variety of tests looking for a significant result. And the old maxim, garbage in, garbage out, always applies. If your data aren't good, no amount of fancy manipulation will produce useful results. It's also important to remember that a result can be statistically significant and still be unimportant. That's because of the way the sampling distribution of X bar works. Remember that the standard deviation of the curve shrinks as the size of your sample increases. For large sample sizes, even very small effects will lie many standard deviations from the mean and will be tagged as significant. On the other hand, if your database is small, the spread will be wide and important effects may not register as significant. One way to protect yourself is to estimate the parameter, compute a confidence interval. That gives you more information than just asking if a change is too large to occur by chance alone. In this program, we've completed our introduction to the 2 most common types of statistical inference, confidence intervals and tests of significance. Within these 2 broad categories are a wide range of specific recipes for handling different types of problems, especially when we don't know the population standard deviation. We'll cook up some of those recipes in the next program.